Hidden Layers. Meet the people behind the data with Uri Elabayev.
Hi, how are you?
Good. How are you?
I'm great. And can you please introduce yourself?
Yes, I'm Leo Leung. I'm part of the compute AI and computing infrastructure product management team.
Amazing. So we start?
Yes.
Right. So we'd like to talk with you about the recent announcements in this field. We saw several new chips, several new ways to make them work together. Can you please elaborate more about that and share with us all the news announcement?
Sure. Yeah, so one of our big infrastructure announcements was our 8th generation of TPUs.
Mm-hmm.
And we've actually introduced 2 chips and systems, the TPU 8T and the TPU 8I. So the 8T is optimized for training workloads. It's probably the closest to like an evolutionary system from the Ironwood TPU of last year. It's massive scale. It's one of the key things it does is it has what we call inter-chip interconnect that allows scale up of up to 9,600 TPUs. So with 19.2 terabits per second of bandwidth. So I think people that aren't familiar with accelerators, that's a massive amount of scale up domain. Yeah. And then it can further scale out using a new network that we just introduced called the Virgo network. And that means that multiple ones of these superpods, a superpod is 9,600 TPUs, can be connected together into a system that's 134,000 TPUs. And that's basically the size of a data center build.
Oh, it's amazing. And can you please share more about the new inference?
Sure.
TPU, this is because this is, I call it a brave decision, because back in the day when you plan a chip, it takes more than 1 year, maybe 2. So you need to look into the future and know that inference will going to be a huge thing. And this time, for the first time, we see 2 chips in 1 year. So I'll be happy to hear your thought about that.
Sure. So the 8T is very focused on having a very large scale up domain and being able to share a lot of processors and memory. The 8I is really meant for agent and inference workloads. And the prime kind of requirement there is the ability for the chips to be able to communicate with each other very quickly with minimal network overhead. So that required multiple things. It required a brand new network architecture. So the T follows what we call a 3D torus, which means that there's 6 network connections per chip so that every chip can see each other in that domain. The 8I uses what we call a board fly architecture. And that's, again, to minimize the amount of network hops from the furthest end of a pod from one end to another. And so that was a brand new network topology. But maybe more importantly, the chip itself is different in that we wanted to increase the amount of memory on the chip as well as make it faster. Right? So we did that on a few different dimensions. We increased the SRAM significantly by 3 times. And then we increased the high bandwidth memory, the HBM, by 50%. So the whole goal there is to have a lot of working memory for the models in order to respond faster, right? So there's something called intermediates where, again, if you've already calculated something in a prior prompt or action, and you can serve it again.
It's like caching?
It's like caching, yeah.
All right.
So if you have a bigger cache, you're able to respond to more requests more quickly.
Oh, amazing.
Yeah.
So we see like there is now a flipping of more usages for the inference. It's something that recent reports said that we are on the edge of make those shifts between training to inference. What do you think will be the future of that? And do you think that you might have more specific or more domain specific chips that are not only for LLM, maybe for VLM or maybe another specific task?
Yeah, it's possible. Amin talked about that a little bit. I think that yes, it took some forecasting to realize that this was going to happen, but I think that's one of the key differentiators for Google is because we have these very, very highly used consumer services that we've embedded AI into, like search, like Gmail, like YouTube, that we have a good sense of how those use cases are developing and how inference is developing. So that definitely informed what we did with the TPU 8i. Going forward, I think, again, that model continues where we look at our own use cases and our applications, but we also look at third-party customers, right? So
who are using the TPUs?
Who are using the TPUs, right? So today, in TK's keynote, we announced Citadel as a customer that uses TPUs. And they're in the financial services business, the quant trading business. So they have a set of, they're very, very quantitative, very mathematical use cases, but that also informs us. Some other customers that use us, there's one in Israel called Lightrix. I don't know if you're familiar with it.
Of course, well known.
Okay, so they use TPUs for text to image, right? Different use case, right? There's a number of drug discovery companies that use TPUs as well. Again, a different use case, which is one of my favorites around trying to accelerate the discovery of drugs, molecules, right? How those work. So all these types of things inform how our current processors work and our next generation. And yeah, that there, I think, is always a possibility for additional different types of hardware that's going to meet the use case.
Interesting. I want to talk about something that Amin also mentioned, is energy. We are getting back to the lower, let's say, basic of the universe. How do you create enough energy in order to make those chips run? And I want to ask you, how big is this part when you are designing the chips or you want to test it? Because sometimes you say, okay, I can make it much stronger, more computation, but it will be less effective energy-wise. So how do you balance these trade-offs?
Yeah, I think that's been true since day one, thinking about it from a system perspective. I think the philosophy has never been, okay, let's just make it as performant as possible and not care, right, about the other attributes. So number one, that's why it's very purposefully designed. TPUs in general have been purposefully designed to do a few things really well. And primarily it's matrix multiplication, which is important for a number of different types of machine learning. But it doesn't do other things, right? It doesn't do ray tracing. It doesn't do other functions that other chips do. And that design and the ultimate chip design, including things like the systolic array architecture, are all purposefully designed to do matrix multiplication really well and very, very efficient, right? Without, for example, tons and tons of memory access for every single function. And so at the chip level, it's more efficient, we believe, than general purpose processors. And then we look at the system, and I talked about the ICI domain, for example, doing it in a way where it's all over copper, right? And minimizing, again, the amount of network switches, equipment, all that type of stuff is part of the design. And then we've been doing liquid cooling for almost a decade now, right? So again, trying to do it efficiently, right? Bring up the amount of processing while keeping the overall thermals moderate. Again, speaks to the system level design, even into the data center design, to keep things efficient.
Fascinating. You mentioned data centers, and this leads me to the next question. In the keynote, it was mentioned that now we're talking about 1 million TPUs connected together, or even more. What do you think it will be the next, let's say, challenges in building those kind of data centers that are, let's say, millions of TPU Now we're talking about 20, maybe 30 gigawatts of what for this. So what's going to be the big next, let's say, challenges in building those kind of infrastructures?
Yeah, I think it's building it with everything in mind, including the environment, right, and including again making sure it's utilized properly, right? All those types of things play into this kind of next wave, right? Because I think that responsibility is important. And I think it has started from the very beginning by having very efficient technology at the base layer and then building up to that scale.
Interesting.
Yeah.
You mentioned the environment and also the energy. And what do you think about data centers in the space? This is a huge infrastructure challenge. The energy is almost free and endless. The environment, if you call it like space pollution with all the satellites, do you think will be the next big phase, or this is something like it's nice as a concept but doesn't make sense, mathematically?
Yeah, I mean, I think power is not infinite.
Oh, the sun, energy, yeah.
Yeah, it's not, and I think it is something that we look at very closely, right, in terms of how to build efficiently and how to build, thoughtfully when it comes to that. Right?
Okay.
Space and power is not infinite.
But it's, let's say, more accessible, much more clean, because other than that, why does it make sense to put GPUs on space? Let's call that one. What do you think about that?
Yeah, I have no idea about GPUs in space or accelerators in space. I think it's I do think that's why the conversation is happening, because power and space is not unlimited, right? Another angle maybe to think about it is how do you distribute the workloads, right? Yes, I think these very large cloud computing environments are part of the equation, but not the only way to solve the problem. Right? So having inference capabilities at the kind of near edge and at the edge is going to be part of the equation as well.
Yeah, you mentioned edge, and I know Google is putting a lot of effort in chips for edge, and also the recent announcement of Gemma 4. We have two models that are specific for edge. By the way, I tried them. They are amazing, doing amazing stuff on local machines. And you mentioned that some of the tasks will be on the edge. But what's your perspective on that? Do you think that small models running on edge device will be capable enough in order to actually give value to users?
I totally think so. Yeah. Yeah. I mean, it's, I will say I was a Pixel user before even joining Google.
Oh, nice.
But I think that there's already some applications. I don't know if you've tried it recently.
Yeah, I've tried. Yeah, there's the just open source the application of the model running locally. So yes.
Yeah. So in multiple cases, you can be completely local to the Pixel device, and it works very well. Right. When it comes to summarization, when it comes to doing intelligent searches of your content on your device, those are things that do not require going to the cloud. Right? So I think finding that balance, doing the research, developing the models, right, that can sit on the edge or the near edge, I think is part of what is going to happen.
Yeah, amazing. We talk mainly until now about hardware, but what about software? I know that many of the developments in Google, but many other companies are focusing using software in order to make the hardware run much faster. If it's in new algorithms, if it's in new, I haven't heard about reinforcement learning in the networking layer. So this is something that you also put effort on that?
Absolutely. Yeah. I mean, I think Amin said it last night. Without the software, there's not much you can do with the hardware, right? So I think it's happening at every layer. So at the actual framework layer, huge focus again on getting maximum productivity out of the chips, but also reliability, right? So a number of pieces of reliability actually come out of the software layer in terms of being able to reroute traffic, right? Being able to, again, maximize the utilization of that hardware.
Mm-hmm.
And then further up the stack, there's a mix of techniques to basically, again, get the most out of the hardware from a bin packing or being able to pack more of the workload into the processors, but also even up to the layer where we have a number of different capabilities. One that's called dynamic workload scheduler that allows customers to basically make a reservation for
Future GPUs.
For future accelerators, where, for example, for a training run, they need 7 days, and they say, okay, just tell me when you have enough accelerators available, and then the job will run by itself, and then it'll shut itself off.
Ah, wow,
right?
amazing.
So you have to get down to that level of granularity, I think, to really wring the most out of the infrastructure and support different customer use cases.
Great, and I want to speak about one of the most common use cases is the agentic use cases. And we see more and more organizations are now trying to build agents, leading to do productions. Google also announced the Gemini Enterprise agent platform.
Agent platform.
Yeah, it's a long name. Yeah, thank you. So I want you to ask you, what is the perspective for this change, but in the infrastructure? And do you understand my question? So
yeah,
a lot of people building agents, but how does it affect the infrastructure?
Yeah, there's a huge effect on the infrastructure. So some of it I talked about when I talked about the AI is there's going to be many, many agents that are operating against the infrastructure.
Mm-hmm.
There's going to be a huge load on the infrastructure. From the AI component of it, the LLM component, but frankly also all the existing applications that are out there are going to have more agents interacting with them.
Yes.
Right? So many of those applications are going to require a refresh or update of their infrastructure in order to handle the load, right? So I think of the agent impact as significant both for accelerators and for traditional CPUs. Another aspect is how do you orchestrate, how do you secure the agent workload? How do you make sure it handles things like idle time, right? Because again, if an agent is asking another agent to do something and that agent is not done, do you continue to use resources during that process? The idea is preferably no, right?
Yeah.
Preferably you idle. If there's an idle, the resources are not consumed and the customer's not paying, right? So that was another announcement we had around something we call GKE Agent Sandbox.
All right.
And what that does is, number one, it will take agent execution and put it in a secure container, right? So if the agent, for example, is generating code, you want to first secure it and inspect it before you release it into production. So that's number one, creating isolation. Number two is scaling fast, right? So again, if an agent kicks off 3 agents that kick off 6 agents, you need environments that can rapidly scale, containers in this case. So Agent Sandbox does that, up to 300 sandboxes a second. And a big, actually, I think they're also based out of Europe, vibe coding platform called Lovable uses them.
From Sweden.
Yeah, they use them already in production. And the numbers are staggering in terms of how many agents they're launching every day. The final aspect is the idle time, right? So being able to quickly snapshot a container so that you can restart it very quickly without using resources. So these are all capabilities of the sandbox. And these are actually underneath the Gemini Enterprise Agent Platform, right? So it's our philosophy to make sure that we're building infrastructure components for companies like Lovable that want to use infrastructure and have the skills to do it. But if you don't, you can use a platform service like Gemini Enterprise and take advantage of the same capabilities.
Yeah, you get the orchestration.
Yeah.
Yeah. You mentioned the CPU and explanation. And now we see like a rising, shining new, let's say, hardware is the CPU. Many companies say that this is something that will going to be very important for agentic. And can you please explain, because sometimes it's not clear to the audience, they get why GPU is important, but why all of a sudden CPU are also important?
Yeah, well, I mean, ultimately agents are going to do a lot of things that applications do, right? So, for example, in a B2B context, if you're entering a customer record, that's a CPU task, right? An accelerator is actually not going to be good at that task, right? It's going to be part of that operation because the agent is going to call an LLM to understand the task, let's say. But then when it executes the task, it's a CPU exercise, right? In the process of agents getting refined, reinforcement learning, those are also CPU tasks because it's training on, again, the same example. If you're doing form filling and capturing customer records, what the agent is doing is testing, simulating that task over and over again in order to understand its efficacy.
Yeah.
Right. And as that reinforcement learning happens and it reaches a point of efficacy that's that is meeting the goal, that is what informs the model training run to happen and adjustment to happen in order to make the model better. But all that stuff in the reinforcement loop is all CPU tasks.
Wow, nice.
So that's why CPUs are becoming interesting again, both for training purposes and for inferencing purposes, because they're required for actually the agents to fulfill what they're supposed to do.
Oh, interesting. So now agents are trying to mimic the task that people are doing.
That's right.
And it's not like you are building a classifier, a dog, a cat, and you need to train, but you actually try to mimic the action of human.
That's right.
And see the entire process of the clicking in, open the file and stuff like that. So this is really interesting to see. And I want to ask you a little bit about the future of infrastructure. Now we are getting the data centers bigger and bigger, and we have more compute, better networking, and we are trying to see that the demand is becoming really, really big as we see. So what do you think will be the future of those infrastructures? Are we going to just keep expanding them? Will hit a limit? Or we find a new way to do the computation, maybe other solution than transformers? So what is your take about the future?
I do believe there's going to be innovations that we don't know about yet, right? In terms of more efficient ways to get to the result. And I think that on the computing side, there's going to be a huge amount of emphasis on efficiency to get more bang for the buck, because the cost structure has to be right too, right? For this business to really fly.
We need ROI.
That's right. That's right. So I think there already is, and there's going to be even more focus there. One thing I forgot to mention is, again, in the software, there's so much efficiency you can wring out, right? So last year we announced something called Inference Gateway at the Kubernetes layer, just to, again, similar to older concepts like caching. Am I using the right resource that has the right key value or cache, for example? Am I using one that's underutilized, right? Because again, up until last year, a lot of the networking technologies were round-robin technologies, which is wrong for the AI use case. Right? So by changing the way we do load balancing, again, 50, 60% increase in efficiency.
Wow.
Right around it. So there's so much more that can be done in the software layer to continue to make even the existing infrastructure work better and higher performance, lower cost.
Right? Yeah, we witnessed, there was a paper from Google about TurboQuant, if I'm correct.
There you go. There's another one.
Improving the KVK. So there's a lot of way to tackle this problem and solve it. So I also agree that the future will be a combination of everything.
Yeah, I think so. And again, that's a great example of if you can really reduce the memory load by 10x, right? That changes things dramatically. Right.
Yeah. But the thing is that humanity will always want more. So we are getting back to the starting point. Thank you. It was really fascinating, really interesting conversation. And thank you for the time.
Absolutely.
Thanks.
Thank you.